So here we have the circuit for majority. So far we've used pictures, or in this case, cookies, in order to represent our model of computing. This is great for us as humans as we try to figure out what's going on and to try to incorporate all of that at an intuitive level. But it's not so great if we're trying to write proofs or make conclusions about our model of computing. So what we're going to need to do is we're going to need to come up with some good formal model for how we can represent a circuit. To get started on this, the first thing we're going to want to do is just brainstorm all of the components we think that we're going to need to have in this circuit. Intuitively, we certainly understand that circuits are going to be made up of gates that are going to perform operations, and then those gates are going to have wires that go from the output of one gate to become the input for another gate. So certainly this means that whatever representation we're going to use for our Boolean circuit model of computing, we're going to want gates in that, and we're also going to want wires connecting those gates. And hopefully this already starts to sound like a graph to you, where we have these locations, these objects, and then these connections among those objects, where the objects in this case are the gates, and the connections are those wires. What we're going to do is we're going to, first of all, be thinking of this as a graph, where gates are nodes and wires are edges. But that's not quite sufficient in order to represent our model of computing. We're going to need a few more things thrown in there. So it's going to be a graph plus some other stuff. So first of all, not all of the gates or nodes in this graph are going to be the same. These are AND gates. These are OR gates. So we're going to need to have some way of labeling our nodes with the operation that they're meant to represent, whether it's AND, OR, NOT, etc. Also, we see here that our Boolean circuit has these inputs and outputs. So we're going to need to somehow include a way for our circuit to receive input and a way for our circuit to receive output. And then for reasons that's going to become clear probably next week, we're also going to want to include in our representation of our circuit the number of bits our circuit is going to receive as input, the number of bits it's going to produce as output, and then also the number of gates that we're going to be using total for our circuit. So now that we've sort of identified all the components that we have in our circuit, let's go ahead and try to bring these together sort of formally so that we can see what exactly a circuit is going to look like with our representation. So what we're going to do is we're going to say that a circuit is going to be represented by a 5-tuple, or a collection of 5 different values. So those values are going to be the set of all of the vertices, which are sort of representing gates, the set of all of the edges, which are going to be representing wires, and then 3 numbers, the number of input bits, the number of output bits, and the number of gates. So we're going to represent a circuit as these 5 values, V, E, N, M, and S, corresponding with those 5 things. So the set of gates V is going to contain N plus S elements, where N in this case is the number of input bits, and S is going to be the number of gates in the circuit. So basically what we're saying is that there's going to be one node in our graph per gate in the circuit, as well as one node in our graph for every single input. So we're kind of going to be considering inputs like a special kind of gate. In addition, what we're going to have is we're going to have this labeling function, where this labeling function, you give it some node of the graph as input, and as output, it's going to tell you what sort of node that represented. So that's what's telling us the role that that gate played in our circuit, whether that's an AND gate, an OR gate, a NOT gate, or an input gate, or so forth. We also are going to have this set E, which is going to be the set of edges or wires in our circuit. So those are going to be defined by ordered pairs, where each item in the ordered pair you can think of as being like a port in one of the gates. So when we look at this ordered pair, G sub I raised to the power K, so we have this subscript I on G and this superscript K, that G sub I is representing which node in the graph we're talking about, that superscript k is what's allowing us to distinguish different ports from one another. So, for example, we could have some gates that have multiple input bits. So that superscript is going to allow us to identify which input we're talking about. So I might say for an AND gate, there are 2 input bits. So when I have an edge going to an AND gate, I'm going to have a superscript of either 0 or 1, depending on which input I want to tie to that. I want to tie that wire to on that AND gate. In addition to having gates or their ports as the endpoints to the edges, we could also have an output as an endpoint to our edge. So you can see here in the definition, we have g sub I to the power k, g sub j to the power l. So those pairs are what are identifying our edges, where g sub I and g sub j are either going to be vertices in the graph, that is gates or inputs, or it's going to be one of our output bits. So edges can go from input to a gate, from a gate to another gate, or from a gate to an output. So let's go back to our majority circuit and talk about how we can represent that majority circuit using this format. So to represent our majority circuit, we're going to need to identify each of those 5 components in that 5 tuple that represents a circuit. So we're definitely going to need our set of vertices or nodes. Recall that those contain the gates and the inputs. We're also going to need our set of edges. Those are representing the wires. And then we need the number of input bits. So in this case, our majority circuit has 3 input bits, so n is going to be equal to 3. And then we need the number of output bits. So in this case, we only have 1 output bit, so m will be 1. And then we need the total number of logical gates that are in our circuit. So in this case, that is going to be 5. So now we have that majority is equal to VE315. So once we define V and E, then we should have our circuit defined. So let's go ahead and identify our set V. So our set V is going to be the set of all gates. It's going to be the nodes in our graph, and that's also going to include the input bits. So in this case, we have 3 input bits, and we have 5 logical gates in our circuit, meaning we better have 8 things that are going to be in this set V. So in this case, our set V is going to contain each of the inputs. So that's going to be x0, x1, and x2. And then it's also going to have the 5 logical gates. So I've called those A0, A1, A2 for each of the AND gates, and then R0, R1 for each of the OR gates. And we have 1, 2, 3, 4, 5, 6, 7, 8 things. So we have everything that we needed in our set of gates V. And now what we need is we need to figure out what the labels are going to be for each of these nodes. We know what role they play. So we need to represent our label function, which we can maybe represent as a table. So we can have our label function, where we can say for each of our gates, we're going to label what type of gate that is. So all of the X's, those are going to be labeled as input, and then all of the A's, those are going to be labeled as AND. And then the R's, those we are going to label as ORs. So this is what our label function looks like. It tells us the role that each of those gates plays in our circuit. Now the final piece that we need are our edges. So I'm not going to go through these exhaustively. You're going to see a slide after this discussion that's going to show you where all of the edges are, or what all the edges are. But I'm just going to get you started to see what the set of edges is going to be. So edges are defined by these pairs, where each item in the pair is going to be a port of a gate or an output. The reason that we say port of a gate and not the gate itself is just in case there are multiple inputs or multiple outputs for the type of gate that we're talking about. if we have this superscript available, that allows us to reference a specific input bit or a specific output bit for a particular gate. Let's go ahead and start with some of the edges that are coming out of input bits. We have an edge that goes from x0, and in this case there is only one output from our input. There is only one value that we're going to get out of a particular input bit. We still need to give that a superscript just for consistency, so I'm just going to give that the superscript of 0. And then that input bit x sub 0, that's going to go in two places. It's going to go to gate a sub 0, so that first AND gate there, and we'll just say that that is going to be input 0. We'll say the top inputs are 0, the bottom inputs are 1, so that'll be input 0 of a sub 0. And then x0 is also going to go to a sub 1, that second AND gate that we see. So it's going to go to port 0 of gate A1. And then we can repeat this for these other gates. So x sub 1, so input bit 1 is going to go to also gate A sub 0, but this time the other port, so we'll call that port 1. And then x sub 1 is also going to go to a sub 2, but this time port 0 of a sub 2. So those are the edges that go out of x0 and out of x1, or the wires that go out of x0 and the wires that go out of x1. We also have outputs going from, let's say, AND gates to OR gates. We have our AND gate, let's take AND gate a sub 0. That only has one output bit, so that's going to be port 0 of the a sub 0 output. And that's going to go to port 0 of that OR gate, R sub 0. And then A1 is going to go to the other port of R sub 0. So we have A1, port 0, output port 0 of A1 is going to go to input port 1 of R0. And now let's look at R1 going to the output bit. So output port 0 of R1 is going to go to input port 0 for Y0, where Y is going to represent our input bit. So this is saying that the output bit 0 is going to come from, its value is going to come from the gate R1. And now we can keep going for all of these wires that we see in our circuit until we've fully developed the circuit. So now we have all of the components of this majority circuit specified. So now that I have the set of all vertices and how they're labeled, I have all of the edges that are available to us, and then I have the number of input bits, the number of output bits, and the number of gates. I have all the information I need to fully specify this circuit. So hopefully you're convinced that we could go back and forth here between pictures of circuits and this representation, and then we could take this graph-like representation and convert that to a picture if we wanted to. Something you might notice with this representation is that not everything that's going to be a valid representation is actually going to make sense as a circuit. So there could be some circuits that you could represent using this graph-type representation where you couldn't actually think of that or consider that to be a circuit. For instance, this representation does not forbid you from having loops in your circuit or cycles in your circuit. It also doesn't guarantee that there's even going to be a path from, say, inputs to the output bit in the circuit and so forth. And that's going to be okay. So we don't have to make it so that we can only represent valid circuits. We just need to make sure that every valid circuit is going to have a representation. So if you think back to like the Python example, it's certainly not every single thing that you could type out that would pass Python syntax is actually going to run. So just because something is syntactically correct as Python does not mean it actually makes sense as an implementation of Python. So you could have a similar thing going on here with our circuit representation.